Albert Einstein's theory of relativity, it feels like it's written in stone, right? For over 100 years, it's been the bedrock of modern physics. But what if there was a tiny crack in that foundation? A simple little error, something hiding in plain sight that maybe, just maybe, even Einstein himself overlooked? Well, today we're diving into that exact pretty wild claim. So, yeah, that's the big question. Could a theory that's been around for a century actually have a simple mistake at its very heart? This is let's call it a controversial question being asked by physicist Miles Mathis. Now, this isn't about claiming Einstein got it all wrong. It's more about making a really subtle, but he argues a really crucial correction. Right, so just to be super clear, the idea here isn't to just, tear down one of the greatest scientific achievements in history. Not at all. The proposal is that by tweaking the framework just a little, we can actually make the whole theory even stronger and more consistent than it already is. All right, section 1, a crack in the foundation. So let's dig in. Where does this whole idea even come from? It all starts by questioning some of the most fundamental ideas in the theory, things that, according to the source, we've kind of taken for granted for over a century. And this quote from Miles Mathis, wow, it really lays it all out there, doesn't it? He's essentially saying the reason we still see some weird inconsistencies in relativity is because nobody, not even Einstein, ever completely 100% understood what the framework was truly about. It's a huge claim, and it really sets the stage for a radical new way of looking at things. Okay, section 2, data versus reality. This is where we get to the absolute heart of the argument. It all boils down to a super important distinction that the source says we've all been missing. A distinction between reality itself and the data we get about that reality. And to get it, we need to talk about a key tool in the physicist's toolbox. Okay, so let's talk about these things called relativistic transforms. Think of them as a special set of math equations that Einstein gave us. And everybody agrees we totally need them. They help us make sense of crazy effects like time slowing down and distances shrinking when things are moving super fast. The whole disagreement here is about one simple thing. What are these equations actually transform? So, here's how pretty much everyone thinks about it now. Let's say there's a spacecraft zooming way out there in deep space. The standard view is that it is literally experiencing funky physics. Its clocks are running slower, its rulers are shorter than ours. The transforms are basically a translation dictionary. They help us convert that weird, funky reality back into something that makes sense to us here on Earth. But the source we're looking at says, hold on, what if we've got that completely backward? In this view, the spacecraft itself is totally normal. Its clocks and its rulers are just like ours. The funkiness isn't happening to the spacecraft, it's happening to the information it sends us. That light signal has to travel across the universe to reach our telescopes, and it gets distorted along the way. So the transform, in this view, isn't for translating reality, it's for unskewing the data. So there it is, the big claim in a nutshell. The whole supposed error is that for 100 years, physicists have been applying this math to the actual object, when they should have been applying it to the information we get from that object. It seems like a tiny shift in thinking, right? But the author claims it leads to massive problems in the math. All right, section 3, the math's hidden contradiction. Now, this isn't just some philosophical debate. According to the source, this conceptual slip-up creates a real mathematical problem, a flat-out contradiction right inside Einstein's own original equations. The whole thing kicks off with this one little equation from special relativity, x equals ct. In Einstein's original work, this is basically used to describe the position of a pulse of light in a system that's moving. The critique here hinges on what that t variable actually represents. But here's where it gets tricky. We all know, Einstein himself said it, that when things move really fast, their clocks run slow, which means the time period, that t prime, actually gets longer, right? A slower tick-tock means more time passes between each tick. This is like day one fundamental relativity. And this is the contradiction the source points to, laid out side by side. On one hand, you've got that equation, x equals ct. That math implies that time and length are directly proportional. If one goes down, the other has to go down too. But Everything we observe and what the theory itself says shows the exact opposite. It shows an inverse relationship. As an object's length contracts, its time period gets longer, its clock slows down. The claim is that this is a major mathematical inconsistency that's been sitting there the whole time. So you're probably thinking, but what about GPS? Isn't that like the slam dunk proof that relativity is correct as is? Well, the source we're examining argues this is actually one of the biggest myths out there. The claim is pretty stunning, that people in the know, the actual engineers, will admit that GPS doesn't really use general relativity in its day-to-day calculations. And according to this analysis, there might be a very simple reason why. According to this analysis, if you just completely ignored the effects of general relativity on a GPS satellite, what would the final error be in figuring out your location? It would be this ridiculously small number, about 1/3 of 1/1000th of a meter. So what does that even mean? Well, to put that into perspective, that's about the width of a single water molecule. A water molecule. The argument here is, come on, are we really navigating our cars with that kind of molecule-level precision? The effect might be real, but for this specific job, it's completely insignificant. And this chart really drives the point home. You've got the best practical accuracy of a normal GPS system, which is around 5 centimeters, give or take. And then you have the error from ignoring relativity, which is, you can't even see it on the chart. It's basically zero in comparison. The conclusion here is that yes, the effect is real, but it's just plain negligible for this application. So let's wrap this up. Section 5, a new view of relativity. Where does all this leave us? Well, the point isn't to burn the whole theory to the ground. It's to say, hey, maybe it's not wrong, just incomplete, or maybe just a little misunderstood. So here's the proposed fixed version. First, relativity is still true, and we absolutely need those transforms. But, and this is the key, the laws of physics are the same for everyone, everywhere in their own little bubble. It's the information that gets warped on its journey to us, not reality itself. The argument is that this one simple change keeps the best parts of relativity, fixes the math, and opens the door for a theory that's even more powerful. And that's what I want to leave you with. You know, if a theory as solid, as established as relativity could have a little secret like this hiding in plain sight for a century, it just makes you wonder, right? What else are we looking at every single day, but not really seeing? What other massive secrets are out there, just waiting for someone to look at the basics from a slightly different angle?